Okay, YouTube, this is my first video in which we're actually going to carry out the complete process for partial fraction decomposition and not just write the decomposition. So let's go and start with what our goal is here. We want to take this complete rational expression, write it as the sum of a bunch of rational expressions, simpler rational expressions. So the first thing we always do with our decomposition is that we factor the denominator here. So I notice that I'd be left with x times x squared plus 2x plus 1. And before I rewrite the top, I just want to kind of just go ahead and say that this would factor further. We'd say x times x plus 1 times x plus 1. So I really get x times x plus 1 squared, and we still have this 5x squared plus 20x plus 6 on the top. So here's where this gets interesting. Actually, I should have written this over here, and I will. We say 5. I'm going to need some room here. Plus 20x plus 6. And this is all over our factored form here. X times a repeated linear factor here. We can see that this is a linear factor that happens twice. So what we're going to do is we're going to start by rewriting our decomposition, and we're going to start by splitting up our factors in the denominator. So I say this one has an x here as our first factor. Our second factor is x plus 1 to the second. So we need to repeat that. We say x plus 1 to the first, and then this one has x plus 1 to the second. We have to put in lesser powers of that repeated factor. And then on the top, what we're going to do is we're just going to put in expressions that are one less in degree than the denominator. We're going to say, well, then this is a first degree thing, so this would be a constant a. This is first degree, so this will be a different constant b, and this is first degree, so we'll choose a different constant c. So here's where this gets interesting. We are going to multiply everything by the least common denominator. And this includes both sides of this equation here. So I'm going to put a big fat set of brackets around this here. I'm going to multiply everything by the LCD. Now when it comes to what the LCD is always going to be this quantity over here that you started with, because this is really the fraction that we're trying to split up, and it should contain all of the factors that were in each of these individually by the time you get to this point. So the LCD is this right here, x times x plus 1 squared. But if we multiply both sides times x plus 1 squared, let's do this. We'd say x times x plus 1 squared. What happens is we get this to cancel completely on the left, and what we get left with is just 5x squared plus 20x plus 6. Sorry to transplant this over to here now. But on the right side, what we're going to do is we're going to distribute this through to each of the terms. And what I want you to see is that when you take this right here, this x over, x times x plus 1 squared over 1 times a over x, what happens is your x's cancel out. And so what you get left with is a times x plus 1 squared. Or in other words, a x plus 1 squared. So now when we take this here, this x times x plus 1 squared times this middle term, this x plus 1 here cancels out with one of these x plus 1 factors, and you get left with b being taken times x plus 1. So we get plus b times x plus 1. And then our last term here, when we take all of this times our c over x plus 1 squared, the x plus 1 squareds cancel out completely. We just get left with cx. So here's what we've done differently from what we've done in the past. We wrote our decomposition, but the only thing we've done here is multiplied both sides by the least common denominator, which is always guaranteed to be this and always wipes out what we have as a denominator on the left side. Now on the right side, we got all of this left over, but what I want you to see is that we have our initial numerator equaling all of this stuff right here. So here's what we're going to do from here. We're going to simplify the right-hand side completely. And what I mean is we get to FOIL out anything that needs to be FOILed, distribute, and then group things up. So on the left side, we have 5x squared plus 20x plus 6. And over here, we get a times x plus 1 squared. Now, given that x plus 1 is, x plus 1 squared is x plus 1 times itself, we get a times now x squared plus 2x plus 1 when we FOIL this out. And then over here, we'll distribute our bx. We get plus bx squared plus bx plus cx. And then I'm going to distribute my a through here. We're going to get it all expanded here. And so I get ax squared plus 2ax plus a plus bx squared plus bx plus cx. So here's what we're going to do now. This is the tricky part. What we're going to do is let's say group by variables to different exponents. Not very good at how to say that here. I'm going to be good at showing this to you, but we're going to start with this. We're just going to get all our x's squared right next to each other. I always start with the biggest power here. So we say ax squared and bx squared. They're both x's squared. So we say ax, I won't skip straight to that. Ax squared plus bx squared. We'll skip straight to what I'm referring to in the next example here, plus bx squared. So now those, I've got those. Now let's start with our x's to the first here. We have 2ax, bx, and cx. So now I'd have plus 2ax plus bx plus cx. So those are gone. Now we'll work with the constants, which is just plus a. So here comes the trick. What we're going to say is that this 5x squared plus 20x plus 6 that we've kept rewriting on the left side here is equal to all this stuff on the right. And because I know that these both have an x squared, then ax squared plus bx squared should give me a total of a plus b of these x squared things. You can also look at this as we factored out the x squared on the side. So I have a plus b of these x squared things. Right here we say how many of these x to the first things do I have? And you can see how we could just rewrite this as 2a plus b plus c of these x things, where I just added my coefficients. Then we say plus a. And the fascinating thing about this is, because this is a one-to-one statement now, I hope you see this, something x squared plus something x to the first plus something constant. The same thing is true about the right side, something x squared, this many x's to the first, and this many constants. What this allows us to do is then to come up with a system of equations. We're going to write our system over here, system. And our first statement we can make here is that this 5 must be the same thing as a plus b. So we say a plus b equals 5. Also, we could say that this 20 here in the middle is equal to, let's see, a 2a plus b plus c is equal to 20. And then our 6, this is kind of nice, is equal to a. So in terms of a, b, and c, if I were to write this as an ordered triple, we already know the a part is 6. Now that I know a is 6, maybe I'll run a substitution and plug it back in up here. We get 6 plus b equals 5. So subtracting 6, we find out that b is negative 1. Negative 1. And then we'd say c. Now when we go solve for c here, I know that a is 6 and b is negative 1, so I get 2 times a plus b plus c is 20. And so we get 6 here, negative 1. So this comes out to be 12 minus 1 plus c is 20. Or in other words, this would imply that 11 plus c is 20. So this must mean that c is 9. I'm going to write that up here. We say 9. So I'll put big fireworks around this, because here's the deal. In the beginning, what we did was we rewrote this as the partial fraction decomposition, this statement right here. And what we were basically admitting was that this original fraction could be rewritten as these three fractions added together, where we split up the factors of the original denominator into their own fractions. But what we were looking for were the values of a, b, and c. And so now that we've got these, what we're going to do, and I'll quarantine this little zone up here, we're going to rewrite this right here, right there. All of this, that's an arrow, is going up here. But instead of a over x plus b over x plus 1 plus c over x plus 1 squared, we're going to write a, which a we were able to determine was equal to 6. B we were able to determine is equal to negative 1. And c is equal to 9. So this right here, this is the completed partial fraction decomposition. And by completed, what I mean is we actually carried out our operations here to go figure out what the values of a, b, and c are. Whereas this was the partial fraction decomposition. This is the completed, because now we have those values. So we're going to look at this again here, except with a new example. So let's take a look at this one here. We'd say, well, factor the denominator. Factoring that first, I want to do that first. I get this, and I can't factor this anymore. So basically what I'm going to do is, I'm going to rewrite this here, 3x squared plus 4x plus 4. Let's go ahead and rewrite our decomposition. So our decomposition is just splitting up our factors here. The difference here you're going to see is that I have an x, and then I have this factor here all to the first, so it's not repeated, but it's quadratic. So I have x squared plus 4. So what makes this problem a little bit different is that we're going to put an a up here, but we have to put not an ax plus b, but just the next letters in the alphabet here, bx plus c. Just because I need a linear thing to go above a quadratic thing. It has to be one less in degree. So now what I have here is on the left, 3x squared plus 4x plus 4. And this is all over x times x squared plus 4. And here's its decomposition. So the LCD, which is this denominator over here, we're going to take both sides times x squared plus 4. So this on the left, when we do that, what I want you to see is x times x squared plus 4. We just get rid of these and we get left with 3x squared plus 4x plus 4. This is always going to happen when you do this partial fraction decomposition. And on the right side, it's worth showing our work here, x times x squared plus 4. So multiplying this through to the first one, a over here, the x's cancel out, and we get left with a times x squared plus 4 plus. Now here, x times x squared plus 4 times this over x squared plus 4. The x squared plus 4 cancel out, and we get left with bx plus c, all of that times the x. So just like we did last time, we're going to expand this right side as much as possible and simplify it. So we have 3x squared plus 4x plus 4 is equal to ax squared plus 4a. Plus, now, ripping this x through here, we get bx squared plus cx. So now I'm going to group these, since it's all simplified there. I'm going to group them by variable to a variable power. So we say x squareds here first. We have a x squared plus b x squared. Now our x is next. I only have x to the first here, so we say cx to the first plus 4a is our constant. So now I would say that let's factor out here the x squared out of these first two terms, or just say that we're using our property of combining like terms. We say I have a plus b total of these x squareds plus c of these x things plus 4a of these constant things. And so now I can say a plus b is equal to 3. So here's our system. A plus b is 3. Also that 4 is equal to c. And also that this 4 is equal to 4a. So my ordered triple here, at least as far as I know, I would say c value, if that's this last value here, is 4. And I know that a, if 4a equals 4, then a equals 1. I'll put a box around that. And now that I know a, I can plug that back in up here. We could say 1 plus b equals 3, so b has to equal 2. So now I know b. And so with this solution pair, what we can do is we can go back to the original decomposition, which said 3x squared plus 4x plus 4 all over x times x squared plus 4. That was equal to a over x plus bx plus c over x squared plus 4. So now we could say that really, plugging in for a, b, and c now, what we really have is the original expression can be rewritten as this over x squared plus 4, but our a value is 1, and our b value and c value respectively are 2 and 4, so we get 2x plus 4. So this right here, if we were to find a common denominator and add it together again, we would get back to what we have right here. Cheers.